Let's do it. Rob 201. We're in our final adventure, understanding Laplace transforms deeply enough that we can, yes, compute solutions to differential equations, but more importantly, understand them from a qualitative point of view. And we did that by looking at roots of a particular denominator. So we'll talk about that. Okay, so Laplace takes a function of time and makes it a function of the Laplace variable s. And s is a complex number. So it has a real part plus I times an imaginary part. It plays nicely with derivatives of functions, and that the Laplace transform of y dot is sy of s minus y at 0 minus, and you can get similar formulas for all of the higher order derivatives. Inputs do not have a past, whereas systems do. So current flowing through a wire, we may set an initial time, but that circuit likely existed before we said T0 was now. And so that's why there's a 0 minus on the signals describing, say, current, position, velocity on the left-hand side of the differential equation, but there is no initial condition for the input signals. We can change them instantaneously any way that we want. We've been working with low-order versions of these. They're called input-output systems or input-output differential equations. So we did y dot, y double dot. We even had a y triple dot. So here's the n dot version. So you'd have a y to the n minus 1 with coefficients, and then you can have your inputs up to some nth derivative. However many derivatives you have, you need that many initial conditions, but the first one is on y not differentiated, and the last one is on y to the n minus 1, and that's because we can always solve for y to the n once we know everything else. When we manipulated the Laplace transform and worked it all out, the solution decomposes nicely and importantly into two parts. One part that depends on how you, the engineer, or how nature is driving the system. And the other one depends upon how the system was initialized. And the fact that you can just add them together and compute them individually, separately, and add them together is called the superposition principle. And I make fun of it and call it the superstition principle as a mnemonic, okay? I can't remember that superposition, but maybe superstition, Halloween, I don't know. Maybe you should call it the Halloween principle. And so if you're looking at y forced, that means you're ignoring the initial conditions or set them equal to 0. And if you're looking at y initial condition, it's the same as setting all of the inputs to 0. And then qualitatively understanding what y is doing, this is why the Laplace transform is useful. It's not so much that we can invert those and get the time domain functions, it's that we can just look at the roots when they are distinct, and then we know that this goes to e to the r1t times a unit step and e to the r2t times a unit step. And there, exponentials, whether they're real or complex, we understand when they are decaying or when they are blowing up. So that's where the qualitative information, and yes, it's all buried in here, but it's less natural to extract it from there than it is when you write down s to the n, capital Y of s plus a to the n minus 1, etc. Less natural. Yep, and this is just showing, once again, the qualitative information. The inverse Laplace transform of that 1 over S minus Rj is e to the Rj, and if it's complex, fine. That just means you get oscillations. And as long as the system is real and the initial conditions are real, the response is going to be a real signal, and that means when you add the various parts up, the imaginary parts are going to cancel, and you'll keep the exponential times sines and cosines. Okay, so that's Laplace for solving differential equations. We're going to start working towards using Laplace as a way to design closed-loop systems, so modifying the differential equation to give it desirable behavior, such as balancing itself. And so we left off here where we said, yeah, differential equations, they can be given in several forms, and this first-order form is pretty common, especially because of two things. One, the solvers like that form. So we would take this input-output differential equation and we would define, say, x1 is y, x2 is y dot, etc., and then rewrite it as a state variable model. But also we know that when we have the robot equations, we naturally get state variable models. And so this is another reason. Okay, so we're going to finish this up and then start moving towards a more abstract view of differential equations and how inputs and outputs interact. So this part is just bookkeeping. If we do Laplace on this is where we left off. Laplace transform of x1 dot, that's s x1 of s minus x1 of 0 minus, and then minus 5 capital X1 of s plus x2 of s plus 7 capital U of s. And we do the same thing for the second row. And here, capital Y of s is just capital X1 of s. And we could solve for y in terms of the initial conditions and the input and get something that looks very similar to this, y forced plus y initial conditions. So that's what we're going to do. But we're not going to do it in this grungy, pre-linear algebra way of writing down linear equations. So here's that same set of differential equations we had right there. There's the initial conditions. And I claim the output of this differential equation in terms of Laplace can be written as something that depends upon the input plus another something that depends on the initial conditions, which is what we have written down here. So let's just see why that's true and how this Si minus A inverse shows up. So our differential equation, x dot equals ax plus bu, y equals cx. We're going to take the Laplace transform of x of t, component by component, and we'll call those capital X1 dot 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 capital Xn. And when they're all stacked up, that's just x of s. So we take the Laplace transform of a vector by just doing the Laplace transform of each component. So there's nothing magical there. And then the derivative is just as we were writing down a moment ago, Laplace transform of x1 dot, s x1 minus x1, 0 minus, dot, dot, dot. Laplace transform of the first derivative of the nth component, s xn of s minus xn of 0 minus. And we just write that as a vector as s times x of s minus the initial condition. So it's, it's kind of easier in this case because we don't have to worry about y double dot is s squared y of s minus s y at 0 minus y dot at 0 minus, okay? We're always using just the first derivative when we deal with x dot equals ax plus bu. So that's kind of nice. We have lots more signals. We have a vector of signals, but they're all to the first derivative, and that is convenient. So to get that result that I had, here's the proposed strategy. I'm going to first solve for x of s in terms of everything, and then we'll note that y is just a vector times x. So y is a scalar, x has n components, so that means y has to be a row vector. Come on, don't jump around on me. Play nice. Play nice. Okay, so y has to be a row vector in this equation. On the simple model that we had written down where y was equal to x1, c would be 1, 0, 0, 0, 0 times x1, x2, x3, dot, dot, xn. So it would just pick off the first component. But maybe y is x2 plus x3, or x2 plus 4 times x3, in which case c would be 0, 1, 4, 0, 0, 0, etc. Okay, so whatever the coefficients are multiplying x1, x2, xn to form y, those coefficients are lumped into the row vector c. Okay, so here's poor man's LaTeX, x dot equals ax plus bu, x at 0 minus equals x0. So this is just making everything larger font, easier to see. And we know x dot is s, capital X of s, minus x at 0 minus. Once again, poor man's notation here, equals a x of s, just doing the linear, and then the b times u of s. So there's the equation. We want to solve for x of s. Well, bring all the x's to the left and put everything else on the right. So s times the n by n identity, I'm going to write that as x of s minus a x of s equals b u of s plus x0 minus. And the reason to put the identity in here is so I can factor out x of s and have it make sense. This is an n by n matrix. The identity is an n by n matrix. Identity times the scalar s is n by n, so this is all n by n. Question to you guys, where else have you seen us writing a parameter times the identity matrix minus a? Where else? First one to answer wins a Buick Skylark, donated by, oh no, that would definitely ruin your financial aid package, wouldn't it, Justin, after everything we went through? I don't think the university would take too kindly to that. Yep, OGC, the Office of General Counsel, would be all over me, so that was just a joke. You're not going to win anything. So where else have you seen, maybe it wasn't called S, but it was a parameter times I minus A. Give me an E. Give me an I. Eigen, cafe. Eigenvector and eigenvalue. Yeah, so you put lambda I minus A times V, and the solution of that equal to 0 got us eigenvectors. So the determinant of Si minus A equals to 0 will give us the eigenvalues of A. So you've seen this type of formula before. But once you have this, Si minus A is just an n by n matrix. What we haven't proved is that it's invertible. as a function of S, and it's because of this identity matrix here. It doesn't matter what A is, it cannot make it uninvertible. So it's always invertible, and we'll just write it as inverse Si minus A B plus inverse Si minus A times X0. So that's a mapping from the forcing terms U and the initial condition to the states. And then we just multiply times the row vector. So this is a column vector times the row vector gets us a scalar. And so there's the Laplace transform of Y of S as a function of the inputs and the initial condition. So forced response, and this is the initial condition response. So it's just like we had earlier. And then there's examples that go through here and work this out for you. Okay, and it's going to get real, too real here pretty soon. Okay, so that finished up the oops. Don't close. Come back to Papa. Where's my damping mechanism? Here it is. That's a spring, that's a damper, and that's a lecture. Open. Okay, so in addition to getting the Laplace transform of this, okay, whoops, that should be a capital Y of S. In addition to that, our big goal is to get to something called transfer functions. Poles and zeros. And a concept called bounded input, bounded output stability that everyone in the know abbreviates as BIBO stability, okay? So you will pretend not to even know the word bounded input, bounded output. You will just use BIBO because you're pros, okay? So that's how we're gonna do that. Okay, so first the notion of systems. Could paste in a nicer diagram, but you have to draw it in your notes, so let me take the time to do that as well. As an input and an output, and then it has a means for transforming the initial conditions into outputs. So I'm just going to write it as ODEs inside here. So like on your laptop, you'll see Intel inside, well, systems, ODEs inside, okay? That's what you have. Same thing. So that's the time domain version. then there's also a Laplace domain, or also called frequency domain version, and that's where we really want to work now. And this is a transfer function that we'll define shortly. That's the word transfer. And we'll denote it as a generic one by G of S. And G is not for Grizzle, okay? It's just what's standard used in the field. G of S and H of S, okay? So it's going to be some function of S. So you have ODEs that take inputs and transform them to outputs. In the frequency domain, that ODE is going to be replaced with a function of S. So transfer function maps U of S, so that's the input in the Laplace domain. To Y of S, and that's the output in the Laplace domain. Okay, so that's the qualitative notion of a transfer function. We'll define it more mathematically, but it's whatever you have to have. So I said, if you know the Laplace transform of the input, you can compute the Laplace transform of the output. Okay, so definition. The transfer function of the input output model. So now I'm going to write down this potentially arbitrarily high order differential equations that we've come to know and love. So y to the n, blah, 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 all the way down to no derivatives equals b0 u of t plus b1 u dot of t plus dot, dot, dot. I don't know why I put t's on the u's and not on the y's. That inconsistency is not good, but so should be t's everywhere or nowhere. Okay. So I'm mixing my metaphors, mixing my notations, okay? So that's not good, but you guys will look through it. You've seen a lot worse from me. So the transfer function of this, so that was just a parenthetical comment, is the rational function G of S, by definition, equal to y of S over u of S. Now I'm going to write a rational function. Here's the denominator. Compare it to the left-hand side of the differential equation. S to the n, a to the n minus 1, s to the n minus 1, a1s plus a0. Okay, and then I'm going to write the highest coefficient first, but you don't have to. And look at this from the right-hand side of the differential equation. Okay. I'm going to give this thing a number, call it star. And this is obtained by taking the Laplace transform of star with all initial conditions equal to 0. And one little note. Look, if I multiply both sides by u of s, so it's really by definition of g of s, y of s is the transfer function times u of s. So it's just multiplication. So it's putting rational in quotes because it can be more general than that, but for everything that's done at the undergraduate level, pretty much g of s and u of s and y of s are always rational functions. They don't have to be, but in practical engineering, 99.99% of the time, they are just rational functions like this one here. Now, first thing to make a note, if somebody gives you this model, you write down the transfer function by inspection. You just copy down the coefficients here, because if you're doing the Laplace transform with s equals 0, this becomes s to the n times capital Y of s, and this is s to the n minus 1 times capital Y of s. And that's all that this is, and the y of s is factored out. And the same thing here, b to the m, s to the m, capital U of s, dot, 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 b0, capital U of s. U of s is factored out. Okay, so that's the transfer function. You get it by inspection. Now, why it's important, you have no idea yet, so we're going to see it's super important and super useful and very easy to manipulate in a design sense, but we just need to get used to get to computing it. So, example. Compute the transfer function and I don't want one with too many numbers in it, and I want the numbers to be nice. Okay, so suppose that's the input-output model. Linear differential equation, constant coefficients, and now I want to write down G of S. Okay, so you guys fill it in, and then I'm going to fill it in, and you see if you get the same thing. It's by inspection. You want to do the mental calculation of Laplace on both sides, factor out capital Y of S and what's left when the initial conditions are 0, and then factor out capital U of S. So this becomes S squared plus 7S minus 6. And then on the numerator, if you want to write them down in reverse order, it doesn't really matter, okay? And that's the same thing as minus 4S plus, doesn't matter. Totally up to you. The software packages pretty much universally or do it like humans. Humans like to write polynomials with the highest number first, and then the next one, the next one, the next one, the next one, all the way down to the lowest order. And the software packages assume they're in that order as well. But, you know, it doesn't change anything. It's just a convention for entering the numbers into a computation. Do you want to do another one, or do you think you got transfer functions down? Online, anybody need to do another one, or you got it? Justin, you feel comfortable with this? Devin, life is good?
I got a little question. So G of S equals, is it the Y of S over U of S, or is it U of S over Y of S?
G of S is Y of S over U of S. So let's just check that out, okay? So which is it? Okay, so let me continue down here and just write this as S squared plus 7S minus 6 times Y of S equals 3 minus 4S times U of S. Okay, so I get Y of S is, and just to be honorary, I'll put them in decreasing order. So whatever is multiplying U, that's G of S. So that's how to remember it. Y equals transfer function times U. And so now if I divide both sides by U of S, I get Y of S over U of S equals minus 4S plus 3 over S squared plus 7S minus 6. And that's, by definition, the transfer function. Okay? So that's the mnemonic. Here's a picture you can keep in your head. So the beautiful thing here is the signal U of S, you know, here it's differentiated and all this crazy stuff and solution is being computed, and then Y of t magically comes out. Here it's very tame. U of S gets multiplied by G of S and we get Y of S, okay? So it's super simple in the in the Laplace domain, in the frequency domain. And so y equals g times u. So this is, when you see this box, what's coming in is multiplying by what's inside. It's like a gain. So the beautiful thing is you now can treat ODEs as a frequency-dependent gain. Crazy, okay? It's really crazy. Okay. The transfer function, of x dot equals ax plus little bu, y is cx, u is scalar, y is scalar, x can have n components, transfer function of that differential equation. It's the same thing. We assume all initial conditions are zero. So I'm going to write it out in that vocabulary just so you've got the two definitions given in slightly different way that reinforces different things. Is the Laplace transform of y of s divided, I don't need a of, Laplace transform y of s divided by the Laplace transform, there's an s in there, transform u of s when all initial conditions are zero. X 0 minus equals 0 n comma 1. And we know what the total solution was. Okay. We had y of s is c times s I minus a inverse b times u of s, and then plus other stuff. And so here's the transfer function. It's what multiplies u. So y of s over g of s is c times s I minus a inverse b. Now this one, yeah, you can't really write it down by inspection. So, cannot compute by inspection. We use software to do that, and I'll show you that in a little bit. But you can imagine we use SymPy, we define the Laplace variable, and then we do a little bit of manipulation. Okay, so, and it doesn't look like it's a rational function of s unless you know a lot about matrix inverses and minors and et cetera, but it is, as we'll see when we do actual computations. Okay. Whoops, where's my systems? Okay, so differential equations, we have input output, so just y and its derivatives equals u and its derivatives, linear combinations. Then we just write down the transfer function by inspection. We have a state variable model, x dot equals ax plus bu, y equals cx. A little more complicated algebra, so we use software to do it. It's okay. So the beauty is, though, we now know how the Laplace transform of the input is modified to become the Laplace transform of the output. We're just multiplying it by a rational function. And if we understand that function well, we'll know how inputs become outputs, and we understand the system. That's the whole point. Okay, so I'm going for now to invite you to read about two things. One, the segue model. So just scan that before Wednesday. And two, linear approximations of nonlinear differential equations. I think that material will be easier for you to kind of scan on your own, and then we can go through a little bit more slowly Bibo stability and manipulating transfer functions. So this is going to allow me to do the following. Talk about poles, zeros, and Bibo stability. Okay, so please scan that material. So for a rational transfer function, g of s, and we're going to write it as a numerator polynomial over a denominator polynomial. I don't know if that looks like a D. It looks like a deformed O, but that's a D. D for denominator, N for numerator. Okay. Now we're going to assume the common factors have been removed. So, okay. With all common factors removed. So if there's an s plus 1 in the numerator and an s plus 1 in the denominator, cancel those puppies. Same for an s squared plus 2s plus 3 if that's in the numerator and in the denominator, cancel them. Get rid of all the common factors. Okay. Removed. poles of G of S are the roots of D of S. And the zeros of the transfer function are the roots of the numerator. So that's poles and zeros. That's just giving names to their polynomials. N is a polynomial, D is a polynomial. They have roots, okay. And we're giving names to them. That's all it is right there. Now, why is this super important? So I'm going to now do something on this little calculation here. So y of s is g of s times u of s. Let's let u of s equal 1 over s. That's the same thing as u of t equals a unit step function. So if I wanted to compute a partial fraction expansion of y of s, well, from u of s, I get 1, I get a s is a factor, 1 over s is in there. But now I use the roots of the denominator of g of s, and those are the poles. So k1 over s minus p1. So we'll call the roots by p now because they have a name, poles. And that works as long as the poles are distinct. We don't have any repeated roots in the denominator. So it's just a partial fraction expansion. Okay, so describe for me the unit step function. Just what does it do?
It's 0 before 0 and then 1.
Yeah. So is it bounded? Yeah, it's not growing like t. It's the prototypical bounded signal. Remember this term, bounded input, bounded output? So I'm just showing you a prototypical one. We could have put sine of t there. That's another bounded one, okay? If I'd used sine, it would have changed this first term because u of s would have had an s squared plus omega squared in it. And so that first term would have changed. But all of these things are the same. And they come from the poles of g of s. So I didn't write that down. Of the poles. So it's just the roots of the denominator, and that's what you need to do a partial fraction expansion. So now what is y of t? coefficient was, and we know we can do it. It's the limit, s goes to 0. We can get all those things. But, okay, so that's a constant term. And then let me just add all these guys up. And I'll use j because I is the imaginary number, right? So we do the inverse Laplace transforms. And this becomes, when there's a minus here, there's a plus here. So this is pjt unit step of t. So this is bounded. Under what conditions does this term converge to 0 as t goes to infinity? So the unit step, that just stays constant. This could be real, in which case we need pj negative, but it could be complex, right? We can have complex roots, in which case we need the real part. So the more general way to write that is the real part of pj is negative. And we'll take our break here pretty soon. We're going to do okay, so we're going to plot real part of S there. J, whoops, not J. I'm not an electrical engineer. I'm now a roboticist. This is I. So this is just the complex plane. And so the real part of the roots being negative, and they always have to occur in complex conjugate pairs if the system is real. This is called the left half plane. Why? Because it's on the left side of the imaginary axis, and this is called the right half plane. Okay. Things that look like e to the pjt here, unit step of t, go to 0 as t goes to infinity. Whereas anything sitting over here, which we could have, e to the pjt, unit step of t, goes to unbounded, as t goes to infinity. They could be oscillating, so they may not have a limit. Okay, they may not have a limit, but the real part of this is positive. Here's the real part. Here's the real part. Here's the real part. It's negative, negative, negative. These guys converge to 0. And these guys don't. And if there were something just on the imaginary axis, they would just be pure oscillation. Let me make these guys. Let's see if I can make them blue. No, overwrite. Okay, so we see a sufficient condition for bounded input. There's our input. It's a unit step, it's bounded. And the output being bounded. So if those guys converge to 0, a sufficient condition is that the real part of the poles are all negative. Because anything over here, that causes things to blow up. Okay, so you can just look at the sign of the real part of the poles, and you know whether bounded inputs are yielding things that's, it might oscillate for a little while and then die out, or it's growing oscillations and you're in trouble. Now, these guys look, they're on the edge, right? They're really close. You move them just a little bit in the left half plane and everything dies out. You put them into the right half plane and they blow up. So that's kind of not very robust. So it's kind of dangerous. I show in the book that if you choose an input that is not a unit step, but is a sinusoid, and it has this frequency, so this would be an omega naught, right? And a minus omega naught. You take the bounded input, instead of making it a unit step, you let it be a sinusoid of the same frequency of a pair of poles sitting on the imaginary axis. The inverse Laplace transform is t times sine omega t. And that's growing, and that's not good. Okay, so when we come back, I'll formally write down a definition of bounded input, bounded output stability, that I've got a differential equation. I put bounded inputs into it. I always get bounded outputs. And you're not going to be surprised when I say it holds if and only if all of the poles are over here in the left half plane, and that these poles are clearly dangerous. And maybe we'll do one quick example to show that those are dangerous as well. Okay, so we'll take our break now. Here's the conceptual part that we're moving into, systems. They're devices that are driven by input signals and produce output signals. So for the Segway, motor torque, good input signal, output signal, kind of your call. Lean angle, making that small, good signal. Speed, good signal. So there's lots of choices for signals. Okay. If you're RLC circuit, you probably take voltages across some of the inductors and currents through some of the capacitors or vice versa as your outputs. And your input is the power source driving the circuit. Okay, so systems transform inputs into outputs. And when the system is described by a linear ODE, you can replace the ODE by a transfer function and understand how the transfer function of the input gets transformed into, how the Laplace transform of the input gets transformed into the Laplace transform of the output. And that's the transfer function. Transfers information. Okay? Transfer functions are rational. So once we cancel all the terms, the poles and zeros are then uniquely defined as the roots of the numerator as the zeros. We're not saying how useful they are. They'll turn out to be quite useful. But for right now, we're focusing on the roots of the denominator. We're giving them a nice name. And those we've seen before, because when we do the partial fraction expansion, we take the roots of the denominator of the Laplace thing and expand it. And here, this is where I got the 1 over s, is because I said the input was a simple bounded input unit step. But there's lots of other bounded inputs, sines and cosines, and you can sine of t squared and all sorts of things, okay? And so then the rest of the terms come from the poles of G of S, and that's why we call them P1, P2, Pn. And so we see exactly what y is doing as soon as we calculate the poles. This term is going to be bounded whenever the input is bounded, and these terms are only going to stay bounded and decay to zero when the real part of the poles are negative. And then what you have to believe, you can go to the book for now, maybe at the end of lecture, if we have a pair of poles on the imaginary axis, that looks bad. Well, it doesn't look very scary at all, actually. But then if you drive it with a sinusoid, you get something called resonance, and t sine of t will pop out, in which case that blows up. Okay, so that's where we left things off. Come on, what are you doing? Whoa, that's a line. I don't know what happened there. I see. Next one won't be so big. Let's make a definition. A system. Let me just write it abstractly. Like this. Is bibostable. Bounded input, bounded I don't want to close that parentheses. Bounded output. And it's almost going to be like an oxymoron, okay? Or a platitude, or an obvious thing. If, whenever U is bounded, we always have Y bounded, okay? If bounded inputs always produce bounded outputs. That's why the name, okay? And the theorem for testing it, the proposition, theorem, whatever. Let's suppose the system is defined by a transfer function G of S. Let me make sure it's rational. Where the degree of n of s is no larger than the degree of the denominator. So you can read in the book why that's a technical condition we need. Almost all systems satisfy that, so it's not really important, but it's for the theorem to hold, it needs to be there. Then it is bibostable. if and only if all poles of G of S have negative real parts. Okay, so stability is trivial to check. As long as you can compute the roots of the denominator of the transfer function, you check their real parts, and then you get stability. So let's just do a few examples. Let's do GA of S equals S plus 2 over S squared minus 1. And that line doesn't need to be so long. And I'll do the factorization so you don't have to, okay? Zero poles and then bibo. Okay, so that's the thing we want to determine. So what are the zeros of this transfer function? They're the roots of the numerator. So I think we don't have too many issues there. So it's minus 2. The poles are the roots of the denominator, plus minus 1. And then is it bibo stable? No. Because of a pole with a positive real part. In this case, plus 1. That one's easy. This one will be easy too, but then we'll get to a little more difficult one. Okay? S plus 1 over S squared minus 1. Look, S plus 1, S plus 1, S minus 1. You have to cancel these, so that's why we're doing this example. Zeros, poles, bibo. So, after we cancel the S plus 1, what are the roots of the numerator? None. So if you write the empty set, fine. I don't care, okay? Just anything to indicate that there are no zeros, okay? What are the poles? Plus 1. Darn it, we should have canceled the other one, so it became bibo, okay? Darn it! We messed up. And it's once again no. 2, 2, pole at plus 1. Right half plane, okay? That blows up at e to the t. Whoops. G sub c of s. 2s minus 4 over s squared plus 2s plus 2. Now, pretend that you're doing this with Julia, okay? So you get the roots of the first one, and then the second one is s plus 1 plus I times s plus 1 minus I. Zeros, poles, bibo. Where are the zeros? They're the roots of the numerator. Are any of those the same as the roots of the denominator? No, there's no canceling has to be done. So the zeros simply, I'll write it as plus 2, but we don't care. The poles now, what are the poles?
-1 minus I, -1 plus I.
Yeah, I'll write it as -1 plus minus I. Yep. What is the real part of those poles? -1. So it's bibo stable. Yes. Real part of -1 plus or minus I equals -1 less than 0. Okay? So that's how you check stability. Yeah, and then I think, let me do this quickly. Let me take g of s equals 1 over s squared plus 1. Okay, so that one really quick. Zeros, none. Poles plus minus I, so it's s squared equals -1. And then bibo, no, do we believe it? And the answer is this. I'm going to take u of t equals sine of t times the unit step. And its Laplace transform is 1 over s squared plus 1. Excuse me, it's s over s squared plus 1. Sine of t is bounded, okay? So this is bounded. So it's a bounded input. Y of s, that's g of s times u of s. So it's s over s squared plus 1 squared. And you have to go to our table. So you have to refer back to our table of Laplace transforms. I don't expect you to have it memorized because I don't even like to memorize the thing, okay? And you get, your notes are probably better. You'll get y of t is t sine of t times unit step of t, which is unbounded. Okay, so poles on the imaginary axis are dangerous because you can hit them with sinusoids of the same frequency. If you read in the textbook, this phenomena of taking something that looks kind of nice and hitting it with the right frequency and having it blow up is called resonance. Whoops. And it yields unbounded behavior. Okay, so we really do want all of our poles in the left half plane. Okay, so that's why poles in the left half plane. Which is same thing, real part, all the poles less than 0. If they're in the right half plane, they clearly blow up exponentially, but even if they're on the imaginary axis, I can choose a different input. In this case, the input was sine of t, and make the output have a t in front. And if I had made it, okay, so that's how stability works. Okay, so this is what I wanted to get to. We're going to start feedback control. Okay, so Laplace transforms, just another way to solve differential equations. And if that's all they gave us, it'd be nice to know them, but not essential to know them. But this notion of transfer functions, oh, is it rich, okay? So let's make our first definition in the feedback control domain. This is a block diagram of a unity feedback system. All it's going to be is a graphical representation of a transfer function. Come on. Oh well, I was going to make everything nice and colored, but probably incapable of keeping that up for very long. Okay, it's feedback because there's a loop here. This is a plus. This is going to be called a reference, R of S. This is going to be called the output, Y of S. And this is going to be called the error signal. So this is reference, error, output. Okay. Where's the word unity? It's because there's a 1 here. I could open up that block and stick in the 1, but nobody does that. But this signal is multiplied by nothing, which means it's unchanged, the same as multiplying by 1. That's what the unity feedback. It's feedback because there is a loop, closed loop, also called closed loop control. This is sometimes called the command, but we're going to call it the reference for now, and then the system has an output, just like we had before. Now, you're looking at that. Well, why do I care about that? Well, let's write down the equations that these things satisfy. E of s, this is just a set of linear equations. It's the reference minus y of s. Okay? Plus, minus this signal. This is called a summer or summing junction. Maybe I'll put the little figure over here. Make the sign super clear. R, Y, E. This is a summing junction. So what am I doing? I'm measuring an output. I would like it to be equal to my reference. I want my water to flow at 1 liter per second. That's my command. I'm measuring my water flow. I'm forming an error. I'm going to act on that, and just a little bit, we'll see how to design this transfer function such that it naturally tries to make this error small, and hence R of S becomes very close to Y of S. Actually, I should say it the other way around. This flow rate becomes very close to its commanded value. That's the whole thing. So that summing junction is key. That's what the loop is about. And then Y of S is equal to G of S times E of S. Well, I'm going to derive something that's fundamental, and it'll become second nature to us in a little while, but not yet. So now Y of S equals G of S. Let me substitute in for E of S. The reference command minus the measured output. That's the error. Okay, this is just linear equation. So Y of S is G of S, R of S, minus G of S times Y of S. I know it seems kind of pedantic to be, okay, once you've given us the equations, Professor Grizzle, we can solve them. I know. But you're probably not used to manipulating rational functions as if they're just any other little symbol, but they are. I want to solve for Y of S in terms of the reference. Okay. I want to know what Y of S is as a function of the reference. Y of S, there's something multiplying R of S to get to Y of S. I want to find the equivalent transfer function for that. That's what I'm going to do. So Y of S plus G of S times Y of S equals G of S times R of S. One plus G of S, and I'll make my Y a little bit better, define a transfer function. Y of s over R of s is G of s over 1 plus G of s. And this looks so tame and so uninteresting and so just like, where did that come from? Oh, it is rich, it is rich, it is rich. Okay, so we're going to calculate a few of these feedback system transfer functions and relate poles of the closed loop system. So this is closed loop. And it's one rational function over 1 plus another rational function. Wow, that's got to be crazy, right? I don't know. Did you guys go to junior high? You got through it, right? Or maybe you just skipped it. You're all so smart, okay? So if I gave you something like 3/4 over 1 plus 3/4. That's a rational number over 1 plus a rational number. Are you frightened by that calculation? Probably not, right? So how would you write that as just a normal rational number? I want to write that as m over n, where m and n are two integers. How do I go from rational over 1 plus rational to just a rational number, a simple rational number, ratio of two integers? How do I do it? They're not being very talkative in the class. Anybody online want to just tell me what the heck do I do to reduce that to one integer over another? It's too easy. You don't want to say it. Come on. Come on. You could do that, and you would get 7 over 4, right? And then you'd have 3 over 4, and then you'd cancel the 4s. Well, there's an easier way. Multiply by 4 over 4, okay? And this is going to be important for us. And then what is that? Do I change anything if I multiply by 4 over 4? No, it's the same number. So that is now 3 over 1 plus 3. And then, yeah. Whoops, this is a 4. Sorry. Did I finish junior high? Maybe not. Maybe I need to go back and do a review. Max, don't turn me in, okay? Okay, that's 3 over 7. Whew. So, let's do an example. Let's do g of s equals 2 over s squared minus 1. Minus plus r of s, y of s. So we need to get through this, and then, oh man, tomorrow, Wednesday, we're going to have fun. Going to be a great week. So y of s over r of s, we have our abstract formula. G of s over 1 plus g of s. Okay. Ooh, rational function over 1 plus rational function. But that's just the same thing as a rational number. So how do I simplify this and write it as a polynomial over a polynomial? Everybody got it? Can you see the polynomial over a polynomial? I multiply the top by s squared minus 1, and I get 2. And I multiply the bottom by s squared minus 1, and I get s squared minus 1 plus 2. And so I get 2 over s squared plus 1. Okay, let's do another one. Let's take, and I'll call this one G2 of S, equals S plus 2 over S squared minus 1. And it's in the same unity feedback loop. There's an abbreviation for feedback loop. Okay? So our output over our command, Laplace transform, is S plus 2 over S squared minus 1 over 1 plus S plus 2 over S squared minus 1. And in the beginning, students go, oh my God, one rational function over another. But as we've seen, it is so easy to clear the denominator and the top and the bottom by just multiplying, because we're always putting g of s over 1 plus g of s. We just multiply by d of s. We just multiply by s squared minus 1 over s squared minus 1. And we get s plus 2 over s squared minus 1. Oh, come on, Grizzle. They're going to have it written down before you do. S squared minus 1 plus s plus 2. And now this becomes s plus 2 over s squared plus s plus 1. Okay. So let's take this. Original G2 of S, S plus 2 over S squared minus 1. Let's just do the poles and the bibo first. We'll come back to zeros again, but we don't need it for the stability, and we know that, so let's just stop computing it. So it's S squared equals 1, and so the poles are plus minus 1. Bibo, no. Darn it. So when we come back to the system, and there's a little bit of vocabulary that I probably should have covered. Suppose I break this loop, so it's not there. So it's just the reference going in and coming out. That's called an open loop system because there's no loop closed, okay? So if I break this, that's open loop. And then I put the loop in and I hook it up to the summing junction. I've closed the loop is the vocabulary. So this is the open loop transfer function. And it's unstable. y of s over r of s and what did that equal? S plus 2 over s squared plus s plus 1. Okay. The poles, grind out your quadratic formula. You get minus a half plus or minus square root of 3 over 2 times I. Now, given that the poles are minus a half plus or minus square root of 3 over 2 times I, is it bibostable or unstable? Yep, Kane, thank you. And now, Kane, now that you've got this, is the closed loop system we're doing now, is it bibostable or not? Everybody do it, yeah. And it's because the real part is negative. And so this is the closed loop. Transfer function, which is bibostable. So this is one of the amazing uses of feedback. We can take a system, depending upon what's here, it can be unstable, and by adding this unity feedback loop, it becomes bibostable. Okay? Now that's just the simplest possible thing you can do. You close the loop, and you don't put a gain in here, you don't put another transfer function, you don't do anything except close the loop. And yeah, wow. In some cases, here we had an unstable open loop system, and we closed the loop, and it became bibostable. Whoa. So I just want to end with one little simple thing, and then we'll pick this up, the story. But the story is going to be how we modify this feedback loop, make it a little bit more complicated so that we can stabilize a broader class of transfer functions. I want to insert a simplified stability test for they didn't copy down. Okay, it's in here. Chapter 10, 6, 7, 8, 9. Simplified stability test. Here we go. This will be helpful to us. So here's the fact. Suppose this is your denominator and you're determining poles. Notice here, I had to apply the quadratic equation. Okay. And then I could get it. There's an easier way to do it. If you have a quadratic, if this coefficient, and this coefficient are all non-zero and all strictly positive, or they all have the same sign, then the poles are automatically have negative real parts. And let's just see why. Well, I'll do it like this. Okay. So the roots are minus R1 and minus R2. So the way I've written it down here, we want R1 and R2 to be positive. The poles are minus R1 and minus R2. So notice that we know enough about multiplication. There's not a 2 here, it's an R1 plus R2 times S plus R1, R2. Okay, so P1 is minus R1, P2 equals minus R2, the poles. We want the poles to be negatives. We want R1 and R2 to be positive. Well, that's if and only if this term is positive and this term is positive. Okay, it's that simple. Now, what about the complex case? S squared plus, so this gives you the roots are minus R plus or minus I times omega. And when you multiply this out, you get S squared, and you get 2 times RS, and then you get R squared plus omega squared. So this is the complex case. Okay, so if R is non-zero, this is non-zero. So if R is positive, so that this is negative, then this is positive. And as long as, if it's complex, omega is non-zero, so this term is automatically positive. Okay, so you can just look at the coefficients and determine Bibo stability when you're so fortunate that the denominator is second order. You don't have to grind around with the quadratic formula. Now, what I'll invite you to do is to look in the textbook for the cubic case. I'll insert it in our summary for Wednesday, but it has a really simple test as well. It's a little bit more complicated. And so my point is, by understanding transfer functions, and we know numerators and denominators, we can do very simple analyses of the denominators and determine Bibo stability with almost no work. Almost none, okay? I didn't even have to calculate a root, and I know that the system is Bibo stable or not, just by looking at the sign of some coefficients. It's stupid easy, okay? It takes practice, but it's so handy to be able to do that, okay?